Okay, good morning, everyone. Can you hear me?
Yes, good morning, Prof.
Right. So I moved to the last chapter of chapter 2, which is this one. Can you see my slide?
Yes, Prof.
Cannot see my slide. Okay. So it's a case study of the real experiment on the correlations theory, analysis, and design in a hot air blower system. So the system under study is the hot air blower system, which is shown here. Okay, so the objective actually to determine the mathematical model of the PT326 hot air blower systems. So we are applying transient response, frequency response, and correlation technique. And then we apply the Prbs generator circuit for 5 maximum length sequence, 15, 31, 63, 127, and 255. And then to verify the mathematical model obtained using a MATLAB software, and then to make comparison between these three techniques. So before we do the experiment, we must understand the function of each element of the process trainer. Okay, and then we collect a data to perform a open loop and closed loop setting for transfer functions. Okay, from the three methods shown. And then to understand the characteristic of the Prbs signal, as well as to verify the answer using MATLAB programming. So as you know that mathematical models can be constructed using two approach. One is analytic approach by derivations, and the other one is experimental approach. And the one that we are going to show now is the non-parametric method of experimental approach. So the system under investigations must follow the procedures of the system ID. First is to accumulate the prior knowledge, and then to design the experiments. Okay, how to connect from one point to another point. Okay, how to collect the data, and then choose the model set and criterion to fit the models, and then calculate the models after we collect the data, and then finally you validate the model. So this is the system under investigations. Okay, is the process trainer. So if you can see here, the hot air blower system is over here. Okay, there is a fan. Okay, that is rotating at this point, and then in front of the fan there is a grill. Okay, is a steel grill, so the fan will blow the air and enter to this heat grill, and then along the way is a hot air. Okay, then this is the exhaust, the exit of the hot air, and then at this point there is a sensor, is a thermistor that measure the hot air temperature, and then it goes to the controller. So we have two controller. One is a continuous controller, PID, and the other one is a two-step control, which is on-off, or we call it as a bang-bang control. Okay. So at this moment, we don't use this one because we are not interested in controller design. We are interested in model this system. So where this hot air blower applied in our daily life, one thing is, have you heard about this air fryer? Is a new way to fry the food. Okay, air fryer is doing the same concept of the hot air blower systems. And then we have to clean up a toilet. So we need a hot air. Okay, they always blow the hot air inside the public toilet to dry up the toilets and others industrial applications. Okay, sorry. So the hot air blower system is equipment that consists of several items. The hot air itself is a process, okay, and the correcting element is the heater, okay, the heater, and then the fan is the motor elements that rotating and blow up the hot air. And then the controlling elements, which is the PID control. Then the comparing element. So comparing element usually refer to the operational amplifier that configured as a comparator, because it will compare the measured temperature from the thermistor that measure the output temperature and then compare with the set value. If you set at 40 degrees of Celsius, so when the thermistor measure at 40 degrees Celsius, the temperature, so automatically the motor element will switch off, okay, because it reached the set value of 40 degrees Celsius, 40 degrees Celsius. Then the thermistor is the detecting element, and then it will be connected to the Wheatstone bridge, which is the measuring element, and then send the value to the amplifier for comparison with the set value. Okay, so this is the schematics of the system: the thermistor, the heater, the power supply, the set value, the indicator, okay, the bridge circuit, and then the measured value indicator. So what is process? The process is the hot air. So the term process is used to describe physicals on a chemical change or the conversion of energy. So there is no chemical change, but just energy from cold air to hot air. Okay, the temperature of air flowing in the tube is the process that concerns. Okay, so we are measuring the temperature of the air. Okay, and in order to do that, we need a detector. Okay, there are so many detector, thermistor, thermocouple, okay, and other temperature sensors. Okay, so we use thermistor because thermistor is very sensitive to the heat. Okay, and always give accurate measurement of hot air temperature, and it's connected to one leg of a bridge. We are using a Wheatstone bridge, so we know that Wheatstone bridge have 4 arms. So one of the arm is connected to the thermistor. So the measuring element is the thermistor probe. Okay, is one arm of the DC bridge, and it is balanced at 40 degrees Celsius. So the bridge output voltage is applied to a DC amplifier, and then produce the voltage varying from 0 to 10 volts. Okay, so that it can measure the change of temperature from 30 Celsius to maximum 60 Celsius. So the output from the measuring element can be monitored at socket Y of the front panel, which is shown previously here. Okay. And the comparing element is the operational amplifier. Okay, the measured value from the bridge and set value are compared with the summing amplifier. Okay, so the internal signals of this equipment have been arranged to be in opposite signs Therefore, the output from the summing amplifier represent deviations. Okay, this deviation is very important. The difference between the output and the input of the set values. So the control element is, as I told you before, we have two type of controller, which is a continuous controller, PID, and then a two-step controller, which is a on-off controller. And the motor element is the actuator, okay, because it's produce movement, motions, okay. The input is electrical, the output is mechanical. So the input is the current or the voltage, and the output is the rotations of the motor to rotate the fan so that the air can be blown out throughout the grid wire, okay, and flow into the tube, okay, and exhaust from the thermistor. And of course, the correcting element is the grill, okay, the wire grid beside the rotation fan, okay, which heats the flowing air. So to measure the data and to observe the data, you need a dynamic signal analyzer, okay. This equipment was available in the laboratory last time, but now it's broke, okay, due to very old system. But we tried to buy a new one, but it's quite expensive. But nowadays, if you buy a National Instrument or any Arduino card, you can simply display on your laptop, okay, instead of buying this equipment, okay, because it's very expensive. So we start the experiment with the correlation technique, okay. So we designed the Prbs, okay, effective random signal of logic 1 levels and logic 0 levels. So can be generated very easily by serial connections or by shift register as shown, okay, with feedback via an exclusive OR gate. Okay, you can see that the OR gate is over here. Okay, so please remember the function of XOR gate because we'll be asked in the test 2, okay, later. And we have a shift register 1, 2, 3, 4, 5, 6, and 7. Okay, of course, all shift register must be provide with the clock pulse, okay, and then the output you can take from the last shift register to be injected to the hot air blower system. Okay, this is the Prbs signals for maximum length sequence of n equal to 31. So what is the value of small n in these signals? 2 power of 5, okay? And small n is equal to 5. So 2 power of 5 is 32 minus 1, 31. Okay, the sequence repeats itself every n equal to 2 power of n minus 1 bit interval. And the bit interval depends on the period of the clock signal as well. So guide for choosing Prbs, please use a very long sequence in conjunction with a very short bit interval or for the Prbs. So experiment setup. So you set the feedback path of the process trainer is disconnected. Will give you open loop setting, and if you connect it, it will be a closed loop setting. As simple as that. So Prbs signal is injected into the system, and then the autocorrelations of the input signal and cross correlation of the input and output signal will be monitored using dynamic signal analyzer, DSA. At the same time, the input and output signals are captured by picoscope for validation purposes. So this is from the dynamic signal analyzer. Okay, from the dynamic signal analyzer, you can see that this is the auto correlations of the Prbs of the input. Okay, similar to the theory that we learned previously. Okay, and this is the auto correlation between the input and the output, the Prbs input and the output signals. Okay, so you can see that we have a impulse there. Okay, like impulse. Okay, so it resembles an exponential graph. Is y is equal to k exponent minus at, and the open loop transfer functions is 1.23 exponent minus 0.52 s plus over s plus 1.42. So it seems that the open loop system have one pole at minus 1.42. Okay. Yeah. Poles minus 1.42, and at the same time they have a time delay which is equal to 0.52 seconds. Is about here. Okay, the time delay 0.52 seconds. So that's why we multiplied with the 1.23 is the gain, multiplied with the time delay element exponent power of minus 0.52. Okay, and then you will get the open loop transfer functions. And then for closed loop results, when we configure as a closed loop, so we captured the autocorrelation function for the input Prbs. Okay, about the same as the previous one, but very narrow. And then we applied closed loop configurations. Okay, for the input of Prbs and the output, you can see that it gives you the decaying sine wave as I mentioned in chapter 2C. Okay, so it is the closed loop transfer function is 7.36 exponent power of minus 0.50 s, meaning that the time delay is 0.5 seconds. Okay, with a complex conjugate poles. Okay, at the bottom for the closed loop system. So we captured 500 data from the input and output signals of the system. Okay, for every maximum length sequence of the Prbs signals. So captured using a picoscope, and then read from the MATLAB for the autocorrelation and cross correlations. Okay, using MATLAB software, you can see that we got a similar waveform for the open loop setting and the closed loop setting. Okay, about similar. Okay. Sorry about the video. The video is not available. Okay, so I don't know why. Maybe the file is corrupted. Never mind. This is the experimental video to capture the data. And then we change from correlation experiment to transient response. Okay, so we inject a step input of 2.4 volts. Okay, with 0.1 Hz is injected to the process trainer for closed loop and open loop setting. Okay, so you can see that we have two signals, which is this is the input, and of course this one is the output. You can see that we have a DC offset over here. Okay, it's supposed to be pulled down. Okay, and you can see that there is a time delay. Can you see that? It takes time from 0 to reach the transient conditions. So there is a time delay for hot air blower system. So this is for the open loop setting. Usually time response is we base on the time constants. Okay, 0.63% of the final value for first order system. But when we configured as the second order closed loop setting, so it is a second order. So you can see that the response is shown as underdamped response. Okay, and of course there are so many errors because we don't apply any controller. Okay, so there is a big error over here. Okay, so that's why we have to apply a PID controller to reduce this steady state error and to improve the transient as well. Okay, so when we do the data from the data, that one is from the experiment, and then we plot the data to verify. So it gives the same shape of the response. Okay, of course we have a time delay. Okay, and this is a typical second order system. Okay, with value of zeta and omega n. Okay, plus some error at the final value. And can see that this is the model structure of the second order system. So it consists of the proportional gain, the zeta value, the natural frequency, and of course the time delay at the exponent part. And the transfer function obtained is quite similar with the previous measurement of the transient response. And then we go to the frequency response. We can see that this one, we need to get signals from the signals generator from 3 millihertz to 1 hertz range of frequency, okay, injected to the system. And from there, we measured the magnitude and the phase difference between the input and the output, okay. And we applied the 20 log for the magnitude, okay, to get the dB and the phase as well for the phase difference. And you can see that from the experiment, okay, this is a real experiment from the oscilloscope. So you can see the phase different and the magnitude different, the amplitude difference, okay, when we apply frequency response experimental. And for open loop, okay, it is
Bijak boleh saya cakap sikit je. Apa sebab kita orang tadi tengah bincang lah pasal belajar pasal belajar space lah, pasal face to face tu. Tu bila macam teringat yang Prof tanya itu. Apa tu yang kau punya gabung pusat kan?
Gabung pusat.
Gabung pusat pentingnya seperti dalam email yang saya hantar itu yang simpan forward pada semua bicara space. Kalau gabung pusat kita boleh teruskan online lagi lah.
Okay, yeah, better.
Kan? Online tapi final exam kena face to face lah.
Online jaga.
So itulah rasanya hari itu kita decide macam tu sebab saya pun dah baca lagu. Cakap tak konsisten.
Sebab kita the only one yang buat hybrid, online tak buat.
Betul. So yang special case untuk yang gabung pusat lah, gabung pusat sebab kita memang arahan kita untuk gabung pusat. So memang kalau tak boleh dapat hybrid, kita buat online terus je lah. Online sampai habis, tapi cuma final exam tu kena face to face lah.
Okay, thank you.
Sorry lah, itu saya tak faham.
Okay.
Banyak lupa.
Okay, alright. Okay, sorry about that. So you can see that what information that we can get from here to model the system is the corner frequency and then the slope of this second order response. So what is the corner frequency over here? Is 1.67 radian per second because this is 1, am I right? So the corner frequency occurred at 1.67 radian per second, and then the slope of this is minus 20 dB per decade. Okay. So it gives you a first order system, okay, from the time response experiment. So this is the first, this one is the open loop setting, first order, but for closed loop settings, so it will give you a second order system. So you can see that observations from the data from the experiments. So this is the omega n, okay. So the omega n is about 1, this is 1, this is 2, 3, 4, 5, okay. So the corner frequency occurred at 5 radian per second, and then the slope of this is minus 40 dB per decade. Okay, so that will give you information that this is a second order system, and of course you can see that from the phase, so it's not settled, it's not settled at final value minus 180 degrees. Why? Because we have a time delay. So that's why when you have a time delay in your model, okay, which is a 0.34 seconds time delay, so the phase is not settled at minus 180, but it goes down and down, okay, below to minus 180 degrees. Then the conclusion of this is for correlation techniques, plant noise will be removed by the correlation operation. That is definitely a very good approach. Okay, we can remove the plant noise and then are able to perform the correlation test while the system is in normal use. Okay, we can still apply correlation even though the process is on. And correlation technique do not provoke an abrupt change in the system compared to step input. But for step input, of course, you have to shut down everything, okay, because a sharp change in the input level can cause a system damage. So that is the disadvantage. Frequency response is time consuming. Many processes do admit sinusoidal inputs in the normal operations. Okay, we can apply some frequency response while the system is on because it didn't disturb the operational process. And then suggestions for this, we should add another one for spectral analysis to compare with the correlation, transient, and frequency response. And then apply parametric approach, which will be in the chapter 3. So I just share with you the chapter 3, okay, chapter 3 slides. Have you got it?
Yes, Prof.
Okay, so this is chapter 3. So chapter 3 is about parametric approach. Okay. So we left the non-parametric approach and then we focus on this. Okay, model structure selections for chapter 3. So basically, parametric model is different from the non-parametric model because parametric model describe system in terms of difference or differential equations. Okay, if you are in continuous time, so you use a differential equation, but if you are in discrete time, we use the difference equations, depending on whether your system is discrete or continuous. To compare the non-parametric model and parametric model, parametric model might have provide a more accurate estimations compared to the non-parametric if users have a prior knowledge about system dynamics, okay, to determine the model orders, time delays, and so on. So step is ID process. No, the process is a very complex process. So we need a procedure in order to apply that. So this is the standard procedures. Okay, so you have to go one by one. Okay, you cannot finally get the final models unless you choose the correct model structure. estimations, parameter estimation, validation, and so on. So choice of model set is very primary and very important, okay? Because if you choose the wrong model set, so it will give non-accurate estimations, okay? So this mathematical description must be studied, must be reviewed, must be compared, okay, in order to set several different model structure that can fit to the unknown data. So criteria of models, you can choose either parametric or non-parametric models. So it is good for you to choose the parametric models. And then linear and non-linear models, of course, it's easy to work in linear model compared to non-linear. But if you face the non-linear models, you have to linearize the non-linear model in order to make your analysis more easy and more accurate. And then you have to choose whether the system under investigation, is it a white box, a gray box, or a black box? We hope for a gray box, at least we know something, some knowledge about the unknown system. So in parametric model, the system described using a limited number of characteristic quantities called parameters of the model. Okay, so while in non-parametric model is characterized by the measurement of a system function at a large number of points. So that is the difference between the parametric and non-parametric. So in real time, every system is nonlinear. Okay, so these nonlinear mathematical models are the most desired ones. So this approach needs a deep understanding of the underlying mechanisms that govern the system behavior. So we must have the good approach, okay, to overcome all the disadvantage, okay, of the system. So comparison between the linear and non-linear. So the developed time of the model is long, takes time. The values of some parameters of the model may be uncertain or can be changed due to the system dynamical, especially motor. Okay, due to the fact that when we obtain or when we derive the model based on empiricals, and after refinements, the model may become too complex to run at the acceptable speed on the computer. So therefore, we use a linear models, okay, which can give you a great success and can be justified by the following facts. Because we apply linearizations, okay, for the mathematical model, and then the output system can be computed for any arbitrary input. And most nonlinear system could be approximated satisfactory in their normal range of operations. That's why for parametric models, we will look into several forms. The first form is a general linear polynomial. The second one is transfer functions. The third one is a zero pole gain. And then the final one is the state space. So the first three, number 1, number 2, and number 3 is based on polynomial models. Okay. State space is different. Okay. It's not polynomial models. So what is a general linear polynomial models? So this model apply only for discrete system. So it's not available for characteristic. Okay. So this system can be described using the following equations. Okay, yk is equal to z power of minus n, g function of z and theta multiplied by the input uk plus h function of z and theta multiplied by ek. uk is the input. Okay, uk is the input. Yk UK is the input, YK is the output. Charging. it again. Okay, UK is the input, YK is the output. Okay, and EK is the noise. Okay, uncertainties, EK. G is the transfer function of the deterministic part of the system. So it relates to the system, while H is the transfer function of the stochastic part of the system. So stochastic part meaning the uncertainty part, the noise, disturbance, and all will go to H, and the system itself will go to G. Okay. So the term Z power of -1 is the backward shift operator in discrete form. Okay, it's like a Laplace operator in continuous form, which is defined by the following equation: Z power of -1 xk is equal to xk minus 1, Z minus 2 xk, xk minus 2, and so on. Okay, Z define the numbers of delay samples between the input and the output. So G and H are rational polynomials as defined by the following equations. Okay, so G is equal to B G is equal to B divided by AF. Okay, so B and A and F is the polynomial. H is equal to C divided by A multiplied by D. So this A, B, C, D is the polynomial, and F as well. Okay. And theta, vector theta is the set of model parameters. Okay, equation in the following slide do not display theta to make the equation easier to read. Okay, so we follow here. So AZ, BZ, CZ, DZ, and FZ is the polynomials as shown here, A, B, C, D, F, where KA, KB, KC, KD, and KF are the model orders. Okay. So if the model orders is 5, meaning that that is the highest, so is the 5th order model, for example. So the following equation describe a general linear polynomial model. Okay, A, Y, K equal to Z minus NB divided by F, UK, C divided by D, EK. Okay, or we can write it as A, Z, Y, K, B over F multiplied by U, K minus N, and C divided by D multiplied by EK. So we can draw it as a block diagram as shown here. Okay, UK, YK, and EK. UK is the input, YK is the output, and EK is the disturbance part. So for input path, UK, B over F. For stochastic part, C divided by D. And for output path, 1 over A. Okay. So a general linear polynomial model provides flexibility. Okay, meaning that we can assume several polynomials as 0. Okay, for both system dynamic and stochastic. Setting one or more of A, C, D, and F equal to 1, create a simpler model such as autoregressive with exogenous term or ARX, or autoregressive moving average with exogenous term RMX, or output error and Box and Jenkins model, which are commonly used in the real world applications. So there are many model structures. So we fix our scope to these 4: ARX, RMAX, output error, and Box and Jenkins. And this model structure is available in the MATLAB toolbox of sysIdEst. So what is ARX model? So ARX model when we assume C, D, and F equal to 1. Okay. So C, D, and F. Okay, so C, D is on the stochastic part. F is on the input path. So just left B and A. So that's why the following equation describe ARX model, which is AY equal to Z BUK plus EK. AY equal to B UK minus N plus EK. So both are the same. Okay, except Z minus N will change to UK minus 1. Right, and then the backward shift operators will make it like this: Z minus N UK equal to UK minus N. That's why you can see that between these two equations, actually the same, but the way we write it as BZ UK minus N. Okay, so it will become like this when you assume C, D, and F equal to 1. Okay. The signal flow graph of the ARX model will become like this. The ARX model is the simplest model incorporating the stimulus signals. However, the ARX model captured some of the stochastic dynamic as part of the system dynamic. Of course, we cannot avoid it. So in this model, the transfer function of the deterministic part G of the system and the transfer function of the stochastic part of the system have the same set poles. Okay. So this coupling can be unrealistic. So the dynamic and stochastic dynamic system do not share the same set of poles all the time. So this disadvantage can be reduced if the signal to noise ratio is high. So meaning that if the signal is good, the noise is low, so we can apply a ARX model. But when disturbance EK of a system is not white noise, the coupling between the deterministic and stochastic dynamic can be biased, the estimation of the ARX model. So the model order can be set higher than the actual model order to minimize the estimation error, especially when the signal to noise ratio is low. Why is low? Because the signal is small and the noise is high. That's why you get S and R low. So however, by increasing the model order, and we can change some dynamic characteristic of the models such as stability part. And in order to get the parameter value from the ARX model, we use a method estimation called least square method. So least square method is the most efficient polynomial estimation because this method solves linear regression equation in the analytical form. Come back to the general linear polynomial model. So we go to the second part, which is the Rmax model. So what is Rmax model? Rmax model is when we assume D and F equal to 1. Okay, so it will become Rmax model. So the equations become A, Y equal to Z, B Z UK plus C Z EK. Okay, and then we change Z minus N to UK minus N. So remember, for Rmax, assume D and F equal to 1. So when you assume D and F equal to 1, so it will give you something like this for the signal flow, Rmax model. Input path B polynomial, stochastic path C polynomial, and output path is 1 over A polynomial. So unlike the ARX model, the system structure of an Rmax model include the stochastic dynamics. Why we use Rmax? Because the SNR is low. The signals is very small, but the noise is very high. That's why we apply Rmax model. We include the stochastic part, the noise part, the uncertainty part in the model. So that's why you get the stochastic dynamics in the model structure of Rmax model. So RMX model are useful when dominating disturbance exists that enter early in the process, such as the input. So RMX model has more flexibility than the ARX model in handling models that contain disturbance. So the identification method of the RMX model is using prediction error, difference from the ARX model, which is use a least square method. So this is the third one. The third one is output error model. How we get output error model is when we assume A, C, and D equal to 1. So the general linear polynomial model reduce the output error model. So it becomes like this, okay? Y equal to Z, B divided by F multiplied by U plus E. And the output error model will, signal flow graph will become like this, okay? Input path is B over F polynomial. Stochastic path, no polynomials. Output path, no polynomials. Okay. And output error model describe the system dynamics separately from the stochastic dynamics. So the output error model does not use any parameters for stimulating and the disturbance characteristics. So identification error method still using prediction error method, which is the same as the RMX model. The last one is the Box and Jenkins. Okay, when we assume A equal to 1, so the model will become Box and Jenkins model as shown in the equations. Okay, so you can see that we have an input, we have the stochastic path, and the output is Y over K. It provides a complete model of a model system. Box and Jenkins model represent disturbance properties separately from the system dynamics. It is useful when you have a disturbance that enter late in the process, such as measurement noise on the output. Okay, and still use a prediction error method for the RMX model. And the last one is the AR model. So AR model is when C, D, F equal to 1 and B equal to 0. Okay, so the generally polynomial model reduced to the AR model as described in the equations, which is over here. Okay, 1 over A, no input. So this one is usually does not include the dynamics between the input and output. Is more suitable for representing signals rather than systems. So usually this is for time series analysis method. Okay, for weather forecast, for predictions, and others, they are using AR model. Okay. Okay, so we stop here until slide 43. Please remind me. We will continue on next Tuesday. Okay. So I will release assignment soon, okay, to all of you. So please read your WhatsApp because I will distribute 5 different topics to 5 students. Okay. Is there any questions? Any questions? No questions. Okay, so I see you next week. We'll share the recorded YouTube link later. Okay, thank you very much.
Thank you, Prof.
Prof.